Alright, today we're going over 3.7, which is implicit differentiation. Implicit differentiation is a more general and concise method of taking derivatives when the function you have is intermixed. In other words, the dependent and independent variables are inseparable. So first, let's take a look at an example where they are separable. So y equals x squared plus 2x. We've learned how to derive this already. On the right side, we would use the power rule to find 2x plus 2. And on the left, we get the derivative of y with respect to x. So I want you to notice a pattern here. When I take the derivative of y as a variable, the derivative of any variable without a leading coefficient that's not squared is 1. So in other words, if I asked you what the derivative of x was, you would say it's 1. Well, likewise, the derivative of y with respect to itself is 1. The derivative of this is 1. But we need to multiply it by the derivative of the inside of the function. So I want you to think of y as a chain rule. So in other words, there is information held within y. It's actually over here. And in order to take the derivative of y, we must also take the derivative of the function inside of y when we're taking it with respect to x. So the derivative of y with respect to x is 1 times dy dx. But up until this point, we haven't worried about the 1. So this is what it looks like up to this point. Now I'd like to show you a problem where the dependent and independent variables are intermixed in such a way to where they cannot be separated. Alright, so here's a function that would be extremely difficult, if not impossible, to separate. In other words, to get y all by itself on one side of the equation and x all by itself on the other side of the equation. So instead of trying to algebraically separate them and wasting a lot of time, what if I want to know what the derivative of this odd function is with respect to x? So I'm going to take the derivative with respect to x of both sides of the function, and it looks something like this. And you may look on the right side and say, I know how to do that one. Yep, and so what you've learned already will apply to implicit differentiation. There's just a few quirks that you'll have to get used to. So the derivative of 2x squared with respect to x using the power rule is 4x. So the right side's finished, let's move to the left side. So applying linearity with derivatives means that I can take any summed or differenced, so any added or subtracted terms, I can take the derivative of them separate from each other. So now I'm going to take d dx of 2x y squared plus the derivative with respect to x of 2y. And let's go ahead and start with the one on the right here. It's a little more straightforward. So the derivative of 2y is actually 2, because using the power rule, y is to the first power, so I bring down the first power, which is 1, and multiply it by 2, and then subtract 1 from y's power, which makes it y to the 0, and so all we're left with here is 2. However, because we're taking the derivative with respect to x and not respect to y, we must respect the fact that y is a function of x. So x is the independent variable, and y is dependent on x. So we have to apply the chain rule here, because we just took the derivative of the outer function, 2y, but there's actually information pertaining to x inside the function y, and according to the chain rule, that means that we have to take the derivative of the inner function and multiply it on to the derivative of the outer function. So the derivative of the outer function is 2 times the derivative of the inner function, which is just dy dx. The inner function is y. We're taking the derivative with respect to x. And what you'll notice is that whenever you take the derivative of y, in any way when doing implicit differentiation, you are going to write dy dx. It's almost a notation that you did take derivative of y with respect to x. So now we're going to look at this right here. We've got 2xy squared. Well, using the constants rule of linearity, I can pull the 2 out front of the derivative, and I look here and I have a product of two terms. The product is in between x and y squared, so I can do the product rule. So I will go ahead and do that now. The first term is x, so first d second d dx of y squared plus second, which is just y squared, d first, which is d dx of x. And then, of course, this is added to this term right here that we took the derivative of. So first d second plus second d first. Now let's solve our derivative. Well, the derivative of y squared using the power rule is going to, oh, and I'm sorry, there's a 2 out in front of here. Let me try to make room for that. 2, oh, what was it? 2 d dx of x. So first d second plus second d first. Oh, and the 2 is being multiplied into the whole product rule. You see why that is because it was multiplied to the whole derivative, so we actually have to put parentheses outside the product rule. Anyways, the derivative with respect to, I'm sorry, this is taking up a lot of space. Let me make more room. Alright, so 2 multiplied by the derivative of this product, which is first d second, that's the derivative with respect to x of y squared, plus second, which is y squared, d first, which is d dx of x. Then we're adding that to the derivative of this, which according to the power rule and the chain rule was 2 dy dx is all equal to 4. Alright, so that's the next step. Now the derivative with respect to x of y squared using the power rule is 2y, but remember, there's information inside of y that we can't ignore that has to do with x, because x is the independent variable. So after we take the derivative of the outer function, which gives us 2y, we must multiply it by the derivative of the inner function, which is dy dx. And so now we're left with 2 all times the quantity x times 2y dy dx, plus we'll do the second part of the product rule, which is y squared times the derivative with respect to x of x, which is just 1. And that's where our parentheses close, added to 2 dy dx equals 4x. Alright, so that's the first part of implicit differentiation where we get all the derivatives taken. Now we're trying to solve algebraically for dy dx, because we're really interested in the derivative of y with respect to x. And so I'm going to clear some room up here, and we'll just do some algebra. So down here we'll multiply the 2 into the 2, that's 4 xy dy dx, plus 2, multiplying the 2, 2 times y squared, plus 2 dy dx, right here, equals 4x. Alright, so we need to get dy dx alone, just like we're solving for x, essentially. So let's move all the non-dy dx terms to the other side. That would be minus 2y squared minus 2y squared. And then we're left with 4xy dy dx plus 2 dy dx equals 4x minus 2y squared. Now we're going to factor dy dx out of both of these expressions. So we get dy dx multiplied by 4xy plus 2 equals 4x minus 2y squared. And then finally, the last step to get dy dx alone is to divide by 4xy plus 2 on both sides. And so we'll go ahead and do that. What we end up with is dy dx equals 4x minus 2y squared all over 4xy plus 2. And the really funky thing about most of the time we use implicit differentiation is that we use it because the derivative wasn't just in terms of x. So with our past derivatives, whatever the derivative was just in terms of x. dy dx equals a function of x. Now dy dx is actually a function of not only x, but also y. So really now we have a derivative that's a function of both x and y. And for that reason, there was no way that we were going to be able to algebraically solve and get y by itself and then take the derivative of x, because the derivative itself is a function of both x and y. So that's the uses for implicit differentiation. Same rules still apply. You still use the power rule, the product rule, quotient rule. You still use the chain rule, which is this is all this is the chain rule. But whenever you take derivative of y, what you're going to do is you're going to multiply on dy dx to whatever that derivative of y is in order to respect the chain rule. I hope this helps. This is particularly difficult, I think. It takes a little bit of time and practice, but if you give yourself grace, you'll get there pretty soon. I hope this helps, and have a great day.